You're watching a Channel 98 NBISD TV production.
Welcome to another edition of That Geometry Show. As always, I'm your funkadelic groovy host, Kevin Corpy. Today is lesson 29. We are nearing the end of our geometric journey together, but we still got a lot of good information left. So, download those worksheets from the website. I work hard creating them, and I create them for you to work along at home. Today we're going to be studying all about special right triangles. So if there ever was a special show, this one by definition is a special show. Special right triangles, let's get right to it. Lesson 29, special right triangles. Today we are going to look at two special right triangles. We're going to look at their side lengths and we're going to look at their angle measure and the correspondence between the two. Now the two triangles are not only very important in geometry, but they do form the basis of the study of coordinate geometry and especially trigonometry, which you'll have in a future math course. So let's kind of review a little bit here. We've talked about triangles a lot on previous episodes. A right triangle, remember, is of course three-sided, and it is a polygon, and it has one angle that has an angle measure of exactly 90 degrees. And we denote the 90-degree angle by drawing the little box down in the corner. All right? Now remember that the sum of all the angles on the interior of a triangle added up to 180 degrees. So if this one here is 90 degrees, the other two have to add to 90, which means that these two angles, in this case angle A and angle B, are complementary. So they also add up to 90 degrees. Let's look a little bit more specifically now. We can label the vertices, the points where the two edges meet, as capital letters. And it's typical to not only call the sides by line segments, like this would be segment CB, but it's also typical to call the sides that are opposite the vertices the same letter notation, but use a lowercase. So if this is capital A, we would call the side opposite little a. If this is angle C, which is the right angle, we can call the side opposite it little c. And same over here, if this is angle B, the side opposite can be little b. Now we also had a theorem on a previous episode that related all three sides of a right triangle, and it was the Pythagorean theorem. Pretty famous. We use it a lot. It says that the sum of the squares of the two shorter sides, in this case a squared plus b squared, is equal to the third longest side, the hypotenuse, squared. So in this case, since c is the longest side, it's c squared. But c might not be what the hypotenuse is labeled in your particular problem, so be very careful when you're plugging in. Now we also denote an angle that's not the right angle sometimes as a capital Greek letter, looks like a zero with the circle through it. We call it theta. It's the capital Greek letter theta. And when we're specifically referring to one of them, in this case we're referring to angle B as theta, we call that one the reference angle. So basically we are referring to one of the right, or one of the angles that is not the right angle in a right triangle. Now we're going to start our study of our two special triangles by looking at the unit square. And what is a unit square? Well, it's a square that has a unit length on one side, which means 1 unit. So it could be one inch, 1 foot, 1 mile, whatever. And then we're going to take a look at its diagonal. Okay? So there we have our unit square. We have 1 and 1, and so that means these two sides are 1 also. And if I look at the diagonal from one corner to the other, I can call it D for diagonal. Now, by the Pythagorean theorem, we can write an expression for the right triangle that's created by the diagonal into the side lengths. We know that 1 squared plus 1 squared equals the hypotenuse, which in this case is the diagonal, squared. So solving for the diagonal length, we get d squared equals 2, or the length of the diagonal is the square root of 2. Now this number that I'm writing down right here has actually brought down an entire group of people known as the Pythagoreans who followed and studied with Pythagoras. People have actually died over the square root of 2. So you might want to do some research on that. We kind of take it for granted today. But more importantly to this episode, we have a right triangle with dimensions 1, 1 as the legs, and the square root of 2 as the hypotenuse. Now let's look at what the angles end up being? We know that this angle is 90 degrees, but remember that a diagonal in a square bisects the angles as well. So if each of these angles originally started out as 90 degrees and the diagonal bisects them, now each of them are half of 90 or 45 degrees. So if I look at this right triangle that's formed by half of the square, I have a right triangle that is a 45, 45, 90 degree triangle, and it corresponds to side lengths of 1, 1, and square root of 2. All right? So I have that redrawn down here. My 1 got cut off. But this basically forms the basis of one of our special right triangles. It's the unit length. Square root of 2 is approximately 1.4. So I have my two smaller legs assigned a unit value of 1. Again, it could be 1 foot, 1 inch, whatever. And the hypotenuse then is going to be the square root of 2. Now what we can do, remember from similar triangles, is we can take this special triangle, 45, 45, 90, and I can multiply all three sides by any number. For instance, if I want to make it larger, I can multiply everything by a 3 all the way around. And that'll give me a 3, 3, and 3 square root of 2 triangle, which is still a 45, 45, 90. Remember, when we dilate or get a similar triangle, we preserve the angle measures. If I wanted to make this one smaller, I could actually multiply by a number smaller than 1, like 1/2. If I multiplied by 1/2 all the way around times 1/2 times 1/2, I would get a 1/2, 1/2, and square root of 2 halves triangle, which would still be a 45, 45, 90, but smaller. So we can summarize that right there. We can multiply all three sides by any non-negative number, and in general we can call that number x. So x could be 3, x could be 1/2, it could be anything that's non-negative. So this brings us to our first theorem about our first special triangle. Special triangle number 1. Here's the theorem. It says in a 45, 45, 90 triangle, which refers to the interior angles measure, the hypotenuse is always square root of 2 times as long as either of the two congruent legs. This is actually an isosceles right triangle. 45, 45, 90. So notice that the largest side is the hypotenuse, and it's always the square root of 2, or 1.4 approximately, times larger than the other sides. So let's see how we can use this expression or this theorem to answer questions. If I have this purple triangle, I want to find the value of z. All right? So in order to be able to use that, we have to show that it's first a 45, 45, 90. So I know it's a right triangle because I have this. One of the other angles is 45, and since the other two angles have to be complementary, they have to add to 90. That means the other one has to be 45. So the two sides opposite the 45s are the smaller sides, and they're what we're calling x up here, or what we call our unit lengths. Well, that's going to be 5, so this is 5. We're trying to find z, which is the hypotenuse. Well, remember the theorem says that the hypotenuse is always the square root of 2 times longer than either one of the legs. So if I'm trying to figure out z, by the theorem, z says, or the theorem says that z is the square root of 2 times the leg length, which is 5. And we can rewrite that as 5 square root of 2. And that's an exact answer. Okay, if you wanted to figure out what that is, you can punch it into your calculator. So that's a pretty easy problem. We're going from a short leg to a hypotenuse, and we multiply by the square root of 2. That leads us to a rule of thumb, something that we can do routinely every time. When we're going from a leg in a 45, 45, 90 right triangle, and we're trying to get to the hypotenuse, all we have to do is do something by the square root of 2. And just like we did in this example, we are going to multiply. So from leg to hypotenuse, from small to large, we multiply by the square root of 2. Okay? It's a rule of thumb. Let's try it out. How can we use that to answer questions that are similar but a little bit different? Well, let's look at this right here. We have a square, it says so right here, and we have the diagonal drawn, and it's 20. We're trying to find the length of the side of a square. So in a square, I know that this is a right angle, and it bisects the other two, so we do have a 45, 45 triangle. But now I'm given the hypotenuse, and I'm trying to find one of the two congruent legs. Well, we kind of have to think backwards here. The theorem says that if I knew this right here, to go from x to 20, I would multiply by the square root of 2. So I can kind of create an algebraic expression if you want. X times the square root of 2 has to equal 20. And now we just solve for x by dividing. So x would equal 20 over the square root of 2. And that's actually what the answer is. But here's a special note. In your trigonometry or pre-calc class, or in your geometry class, or in mathematics at high school in general, teachers tend not to like a radical in the denominator. So one way to get rid of that is to multiply by a clever form of 1. 1 is the identity element for multiplication. So I can multiply by something that's equal to 1 without changing the value. And that expression is going to precisely be the radical in the denominator, square root of 2, over itself. Now by multiplying, I get 20, the square root of 2, and the square root of 2 times the square root of 2 is the square root of 2 squared, which is in fact 2. And now I can simplify. I have 20 halves, or 20 divided by 2, which equals 10 times the square root of 2. So 10 times the square root of 2 is equivalent to 20 over the square root of 2, but 10 square root of 2 looks much prettier. So that's what x ends up being. Well, now we can verify. We can actually work backwards. If I started with 10 square root of 2, which is one of the shorter legs, to get from here to 20, the theorem says to multiply by the square root of 2. So 10 square root of 2 times the square root of 2, well, that's going to be 10 times 2, which is in fact 20. So I've checked and I've got it right. Okay, so what did we essentially do? I essentially took the 20, and instead of multiplying by the square root of 2 to get to the hypotenuse, I went from the hypotenuse to a shorter leg. I essentially divided by the square root of 2. So you can use the theorem in reverse. So here's your other rule of thumb. In a 45, 45, 90 triangle, when you're going from a hypotenuse, the long part, to the leg, the shorter part, we are going to divide, do the inverse operation by the square root of 2. Pretty easy. All right, let's take a real short break to watch some very valuable public service announcements, but do not go away. Come right back here, because today we're having a 2-for-1 deal. 2 special triangles for the price of 1.
All right, guys and gals, MBHS, I'm Coach Fair. I also teach math here, and we've got the tax test coming up. I'm representing the teacher that's prepared you for the tax test. I'd like to now introduce Kevin Corpy. He's also a math teacher. He's representing the math problems on the tax test, and I'm going to show you how to tackle them. Whoa! Whoa! It's not a good time to be a math tax problem.
Welcome back to That Geometry Show. I'm your host, Kevin Corpy. Today we're talking about special right triangles. We got one down, got one to go. Let's get right to it. All right, to get our second special triangle, we're going to start with an equilateral triangle here that has a side length of 2 units. So I've marked one of them here as 2. This one would also be 2, and the length of the entire bottom, if you want to show it, would also be 2. Okay, so they are all congruent. Now what we're going to do is we're going to drop an altitude, a perpendicular, straight down from the top vertex to the bottom. Now that is not only an altitude in an equilateral triangle. Remember, it had 2 other special properties. First of all, it was a median, which means it bisected the length of the other side. So if the entire side length down here was 2, now each of these lengths are 1 unit. So an altitude was a median in an equilateral triangle, and it bisected the angle. So if this is an equilateral triangle, all the angles are the same. So this was originally 60, this was also 60, and the other one was also 60. But if this altitude bisects it, now I have two angles up here that are congruent to each other, but they're half of 60 or 30. So now what I can do is I can look at the individual right triangles, either one of them, and try and find what the length of this altitude is, which I'll call h. Okay? So let's focus in on this right triangle now. It's going to be a right triangle, but my angles are now 30, 60, and 90 instead of 45, 45. Okay? Let's see if we can figure out what the other length is, h. And we're going to use the Pythagorean theorem. H, the altitude, is one of the shorter legs, and so is the number 1. So I get 1 squared plus h squared equals the hypotenuse, which is 2 squared. So I get h squared equals 2 squared, which is 4, minus 1. That's 3. So if I take the square root of both sides, I get h, the altitude, is the square root of 3 units long. So now I have created my other special right triangle. It's going to be the triangle, the right triangle, that is the 30, 60, 90 triangle, and its side lengths are going to be 1, square root of 3, 2. Okay? So here's the theorem that talks about that one. In a 30, 60, 90 triangle, the corresponding side lengths are 1, square root of 3, and 2. So notice that the angles are listed now in increasing order. 30 is the smallest angle, then comes 60, then 90. The side lengths correspond. They're also in increasing order. 1 is the smallest, or unit length. The square root of 3 is about 1.7, and 2 is, of course, larger than 1.7. Now, it's important for this triangle to get your numbers correct. For the 45, 45, 90, the two legs were congruent, so you didn't have to pay as much attention in labeling the sides. But here they are different. So remember about triangles that the preservation of the angles and the corresponding sides is important. In other words, opposite 30, the smallest angle, lives the smallest side, which we usually assign a unit value of 1. The next largest angle is 60 degrees. Opposite it is the next largest side, square root of 3, which is about 1.7. And opposite the largest angle, which is the right angle, 90, is the largest side, the hypotenuse, which is a 2. So we have to make sure that we're looking at the correct sides that correspond to the correct angles. Okay? Now I'm going to show you how we're going to use this. We can basically do the same thing with the 45, 45, 90. I can take any number and dilate this to make it smaller or to make it bigger, which is going to give me a similar triangle. So if I wanted to make it twice as big, I'll just multiply everything by 2. And that'll give me a 2 square root of 3, 4 right triangle. But I'm still going to preserve the angles. This is still a 30, 60, 90 right triangle. So if you want to think about it in terms of x, like we did for the 45, 45, 90, we will assign our smallest side, x. The next largest side is opposite 60, and it's the square root of 3 times larger than this. So this would be the square root of 3 times x, or x square root of 3. And the hypotenuse is always twice as big as this other side, so this would be 2x. Okay? That might be worth redrawing off to the side here. 30, 60, 90. We have x. Then we have x square root of 3. We need to make this like that. There we go. X square root of 3 and 2x. Scoot it over there. Okay? Now, I'm going to show you how to use this. There's a little bit of skill involved because we can't easily go from any side to the other. We're going to have to go through a common side just to make the calculations a little bit easier. And I'll show you what I mean. Okay, in this example here, we want to find the value of y and we want to find the value of z. Well, we're starting off with a rectangle. So we know that we have a right angle down here in the corner and we have a diagonal. Now the diagonal does not bisect the angles in a rectangle, only in a square. But we do know that this angle right here is 30 degrees. And we know that the top and the bottom of a rectangle are parallel. So alternate interior angles, remember, this angle and this angle here are congruent. So I also know that this angle is 30 degrees. So I can now look at this right triangle formed in the bottom of the rectangle. So now I have a 30 degrees. This is 90, so this is the complement of 30, which has to be 60. Well, now I have my 30, 60, 90 triangle. So let's see if we can find y. And y is going to be the one we want to find first. Why, you ask? Well, if we get in the habit in our 30, 60, 90s of identifying what the smallest side is, which is our unit length, it's going to make our calculations easier. And that side is always opposite the smallest 30-degree angle. So y is our smallest side, or the unit length side. Okay? Now from there, it's pretty easy. If I want to go from the smallest side to the other leg, remember I just multiply by the square root of 3. And if I want to go from the smallest side to the hypotenuse, it's twice as big, so I just multiply by 2. Okay? So let's see what we can do to answer the question. I'm not given y. I'm giving the hypotenuse. So just like we did for the 45, 45, 90, if I'm trying to go from the hypotenuse back to the smaller side, instead of multiplying by 2, I need to make it smaller. So I'm going to do the inverse. I'm going to divide by 2. So you can think of it as an algebraic expression. If you're starting with y to get to 9, you multiply by 2. So 2y equals 9, which means y equals 9 divided by 2. And that's the answer. That's around 4.5. Now that I know the unit side, which is 4.5, or I'm actually going to leave it as 9/2, it's real easy to go to any of the other two sides. Let's verify quickly. From here to the hypotenuse, I multiply by 2. 9/2 times 2 is 9. Or more importantly now, to find z, to go from y to z, from one leg to the other, I multiply by the square root of 3. So z is going to equal my unit length, 9/2, times the square root of 3. And to make the calculations easier, you can put it over 1. So we end up with 9 square root of 3 over 2, which is a simplified exact answer. And if you have your calculator, you can see that's about 7.794. All right. Here's a rule of thumb. And it's not so easy a rule of thumb. It's going to take a little more practice than the 45, 45, 90. Memorize the unit lengths. You got a 1, you got a square root of 3, and you got a 2. And appropriately multiply or divide by the correct value to get from one side to the other. I can tell you, though, that it's going to be easier to go through the smallest side, which is your unit side, opposite your 30-degree angle. Okay? If you can go through the smallest side, then everything else is a lot easier. Let me show you what I mean. This diagram here can be kind of helpful, but it can also be kind of confusing. Notice I have my 30, 60, 90. Opposite the 30 is my unit length. So let's say I'm starting here with x. Could be anything. Could be 1, it could be 5 now. If I know this and I'm trying to go to the hypotenuse, I'm going to follow the arrow. From here to the hypotenuse, I multiply by 2. So this is going to give me 2x. If I'm starting with this, let's say it's 2x, and I want to go back, I just do the inverse. I divide by 2. 2x divided by 2 is back to x. If I'm starting with the unit side and I'm trying to go to the other leg, I'll follow this arrow. I multiply by the square root of 3, and I get x square root of 3. Or if I happen to start with this side and I want to go back to the other leg, I divide by the square root of 3. So x square root of 3 divided by the square root of 3 gets me right back to x. So I've created this kind of loop here. Now what you can do, and if you're really good, you can do this. It's going from this side length, the square root of 3 side length, the one opposite 60, to the hypotenuse. You're going to have to do a sequence of operations. You're going to have to multiply and divide. But it's kind of confusing. Do you multiply by the square root of 2 or do you divide by the square root of 2? And what do you do with that square root of 3? So I think most teachers would probably warn against doing that unless you've worked enough of these that you just have the habit of knowing what to do correctly. So regardless of which side you're given, if you always go back and get to the unit length first, then you've kind of made your decisions a lot more limited, and that's going to help you be more successful. For example, let's look at this problem here. I actually have this one kind of worked out already. We're trying to find the value of x right here. So notice that I do have a 60 degrees, and that's 90 degrees. So that means the other angle up here has to be the complement of 60, which is 30. The side opposite 30 is my shortest side, and that's y. If I'm trying to find the value of x, I could go, if I'm brave and daring, straight from here to here, from the side opposite 60 to the hypotenuse. But I'm not going to do that. I'm going to first find what y is. I'm going to go from my short leg to the shortest leg. And what do I do in doing that? Well, let's go back to the diagram here. If I have the side opposite 60 and I'm trying to go back to the short leg, I divide by the square root of 3 right here. So if I divide by the square root of 3, I get 5 square root of 6. Let me actually do the work right here. We won't follow that. I get 5 square root of 6. To go from here, I divide by the square root of 3. And we need to rationalize that now. So this is where a little bit of the math comes in. We're going to have to multiply again by the square root of 3 over the square root of 3. And that's going to give us 5 square root of 18 over 3. Now the square root of 18 actually simplifies. It has a perfect square factor, namely 9. So I can write that as 3 square root of 2. So this becomes 15 times the square root of 2 over 3. And then 15 thirds is 5. So there's a little bit of work in getting to 5 square root of 2. But that's what this is. It's 5 square root of 2. Now that I have my shortest side, now it's a lot easier to go to the hypotenuse, which is always twice the length of the shortest side in the 30, 60, 90. So now times 2. So x is going to equal my shortest side, 5 square root of 2, times 2, which is 10 square root of 2. So going through the shortest side definitely has its benefits. All right, it's time for the say what? Say what? And we have a nice little application of the 30, 60, 90 triangles today. Kind of cute if you want to go that route. We got this guy Charles. He's up in his room, and he's looking down out of his window, and he sees his dog Max. His Max dog is looking right back at him. But here's what we know. Charles happens to have instrumentation in his room that measures angles of depression. So what is an angle of depression? Well, if he's looking straight out, the angle that he has to look down from the horizontal is called the angle of depression, and it makes a 30-degree angle with horizontal. On the other hand, Max, if his dog Max was down here looking at the horizontal, the angle that he had to do to look up would be called the angle of elevation. And in this case, the angle of elevation and the angle of depression are alternate interior angles, so they are congruent. So I know that this angle is 30 degrees. Well, what we're trying to figure out is if Charles is 50 feet up, how far away is his dog Max from the base of the window? We're going to call that x. Well, this is an application of our special right triangles. Because I have a right triangle here, I have 30 degrees, so this is going to be 60 degrees. So opposite the 30 degrees, I have my 50, which is my unit length. It's my smallest side length. So if I'm trying to find x, that's going to be the side, the other leg of the triangle. And remember what we do to go from the smallest side to the other leg? We multiply by the square root of 3. So once we know that, the problem's pretty easy. We know that x then is equal to the length of that side, 50, times the square root of 3, which if you work that out on the calculator, comes out to be approximately 87, I believe. And we need to put our units here, feet above window, so this is going to be feet away. So Max, the dog, is about 50 feet away from the base of the window. So come on, Max. Dinner time. All right, that's 2 very special right triangles we talked about on today's show. They're very similar, but very different in terms of the proportion of the sides. It's something that's worth memorizing before you start working examples, and develop enough proficiency working the 2 types of examples so that when you see them on your test in geometry class or on the tax test, you're not going to be haunted by them or fooled by them or intimidated by them. You'll be able to tackle them with agility and confidence. So until next time, I'm your host, Kevin Corpy, and I will catch you on the flip side.